Okay, so I think we are recording now. Without a further ado, I will hand over to Rakvi, and to the rest, everyone here now and on YouTube, enjoy this fascinating journey into the world of elliptic curves. I see you.
Thanks, Pimbode. Hi, everyone. So, I'm Rakvi. I can write my name here. And I'll be presenting these series of lectures to you, which are mostly about elliptic cryptography. So, today's lecture, yeah, and before we start, I would just like to say if you have any questions at any moment, if something I write is not, if my handwriting is not clear, or if my voice is not clear, or if something I say doesn't make any sense, just please feel free to ask at that time. Okay, you can unmute yourself or ask, or you can type it in the chat, whatever you prefer, but I would really encourage you to just unmute and ask. Okay, and feel free to interrupt. I mean, it's completely fine. um right, so that's my name, and today's lecture is so I'll be following this textbook for this mini course. It's called Guide to Elliptic Curve Cryptography, and it's by, so the authors are Daryl Hankerson, Alfred Menezes, I hope I'm pronouncing their name right, and Scott Vanstone. All right, and today's lecture is mostly on first chapter of this book. So after we after my lecture ends here, I would really encourage you to check out this book for more details and clarification on some technical stuff. Right, they have details about some, I mean, some of the topics that we'll see. So yeah, I would really encourage you to check out this book. uh, okay, so without further delay, let's start with elliptic curve cryptography. So since today is the first lecture, let me take this opportunity to discuss a bit about cryptography and why do we care so much about these things in the world we live in. So so what's the basic idea, right? The basic premise is, let's say there are two people, A and B, and what they're trying to do is they're trying to communicate to each other. So they're trying to send messages to each other, right? And this is a very general setting, right? This can be anything. I mean, these can be two, let's say, security officials trying to talk to each other about some highly classified information, or this can be like our simple day-to-day lives, right? Like I'm trying to buy something from Amazon, and I'm trying to enter my uh, credit card or debit card details into this third party payment site, right? That's also communication. Or like pretty much anything, right? Like online transaction, or for that matter, like if you're trying to buy cryptocurrencies, or if you're trying to make any online deal, these are also. Or if you're trying to, like if you're in an ATM and you're trying to use your debit card to get some cash out, that's also a sort of communication. Emails, everybody uses these things, right? WhatsApp. So these things are, like, this is quite a general setting. So the idea is that two people are trying to communicate to each other, and there is a third person here. Let me call it E. E stands for eavesdropping, right? So the idea is that what two people are trying to communicate, that's is supposed to be confidential and secure between them. There is a third person who is trying to eavesdrop, right, and read the message. And the idea is to prevent this from happening, right? We don't want these messages to leak out. We want to maintain confidentiality in our communication, right? So that's why what A and B can try to do is whatever their original message is. So let's say their original message is, like for example, A is trying to say to B that I am at Rose Park, let's say. For example, this can be a message, right? This can be a text message, this can be a figure, this can be some documents, these can be some videos, these can be some pictures, or these can simply just be numbers, that can be coordinates, right? Or anything, right? I have just given an example of a message. This is what we call a message. And in most of the cryptos, uh, in most of the protocols or most of the cryptographic algorithms that we will see, you will often notice that the idea is to, we often try to convert these text messages into some sort of a number, right? So that is always there, but let's just start with a like a very basic example. So this can be a message, right? I am at Rose Park. And if they try to communicate it like this only, like it, and if the channel is not secure enough, the other persons who are not supposed to know that A is supposed to be at Rose Park, they will come to know, and obviously everything will be jeopardized. So what can be done to mitigate this is, you can try to crypt your message, right? Or some sort of transform your message, so that even though a person reads it, they are not immediately able to figure out what the original message is. So a very basic, again, a very basic thing is, so for example, I, right? So like a basic cipher, like this is always my favorite example, because I'm pretty sure most of us here as kids really enjoyed doing these things. At least I did. When I first discovered this, I was really thrilled. So what you can do is, to your original message, you can try to add, like you can try to add three letters to every letter in your message, right? For example, let's see, plus 3, right? So for example, if you try to add three letters to I, you will get to L. Okay, so let's see. So I will become L, because I, J, K, L, right? And then A will become D, M will become P, and so on, right? So D, uh, W, and R will become U. I'm just adding three letters to everything, right? So P will, and similarly, we'll have something for P also. So P will become S, A is already D, and then R is U, and then K is N. So this becomes our new message, right? Let me call this, so this is what we call encrypted message. So instead of sending the original message to B, what A will now do is try to send this encrypted message to B, right? And immediately it's not very obvious what A is trying to say, right? Therefore, even the idea is, even if E tries to listen it or somehow has an access, we will not be in so much danger, right? And then when B receives this message, what B can do is apply this key reverse, right? And then try to recover the message. So what will B do is, so B's job is to decrypt this message. So the idea is to apply the key, and in this case, key is go back three letters, right? And then you can recover the original message, which was I am at Rose Park, right? So this is a perfectly good, basic, simple example of how a crypto system works, or how these cryptographic protocols work. But what's the catch here? The catch is that we want our algorithms to be robust enough, to be secure enough, so that it's not easy to break it down, right? The Obviously, with these kind of things, the challenge is that it's quite easy to break these things down, right? Uh, like this basic cipher, it can be made more complicated, right? So let me write this down. So the problem is this is easy to break. So this, even in this setting, this can be made more challenging, right? For example, we can use, instead of a fixed key, like add 3 letters, which is a fixed key, right? To every letter, you are adding 3 letters. You can make this into a rotating key, right? For example, you start with adding 3 letters, and then for next, you add 4 letters, 5 letters, 6 letters, and so on. So you can convert this into a rotating key, which makes it even harder. But even then, it's like, with the kind of technology we have at our disposal these days, these things are quite easy to break down, right? All you have to do is look for the repeating. If your message is long enough, all you have to do is just look for the most frequent letter, which often turns out to be E. And then you can try to break the key from that, right? It's only as good as your weakest or strongest letter, whichever way you think about it. Right. So, yeah, the problem is this easy to break. So, we want more sophisticated algorithms. When I'll discuss algorithm, so this thing was an example of something called, so this ciphering algorithm, or this cipher, let me just call it cipher, was an example of something that we call symmetric key cryptography. So symmetric key comes from the so the idea is that whatever key you are using, both the parties have information to that key, right? And they both, yeah, so they both use it. So a general symmetric key cryptography would look something like this. So again, you have two parties, A and B, and then they are trying to communicate with each other. So what A does, is, and there is a secret, there is a key, let's say K, that both parties know. All right. So if your message is M, what will A do? So the message is, let's say, M, that they're trying to send to each other. So what will A do is A will use an encryption algorithm to do the following. So it will apply this, let me say this algorithm is ENC, that uses this message and this K. So it will apply that encryption algorithm to create a ciphertext, right? To go back to our example, our M was this line, I am at Rose Park. The encryption algorithm was that you add 3 letters to every letter in your message, and then you create this ciphertext, right? This encrypted message, also known as ciphertext. So this is example of C, right? And this is an example of an encryption. Obviously, in real life, we use more sophisticated things, but just to illustrate. So A will use an encryption algorithm to create this ciphertext C, right? And then this C will be transmitted to B. So B will receive C. B will receive C. And then what will B do is B will apply a decryption algorithm. Let me call it decrypt. Let, let me use the full word. B will have a certain decryption algorithm that will again use this key, and it will now be applied to this C to recover this original message, right? And then recover. So this is a basic symmetric key cryptography, how it works. And again, to add more authenticity, to add more layers of security, what one can do is you can create your own signatures. You can create your own digital signatures, and then you can tag these things to make sure, so that B can verify that the message that B received was indeed sent from A, and not from an imposter or from a third party, which can be potentially like malefic or dangerous, so to say. So yeah, these you can always add extra layers of security to these things. But this is a basic idea, right? And one key feature about this symmetric key cryptography is that the key which is used to decrypt or encode or decode the message is available to both the parties. So both the parties have this key and they have this information, right? So what is I mean, even though your algorithm may be perfect, not perfect in the say, let's say it's quite robust, it's difficult to break and everything. But even then, managing these keys can be a challenge. Okay. So one challenging thing about this symmetric key cryptography is managing these keys can require a lot of, let's say, computing memory. This can be one of the challenges, right? So let's say like at a time you're not just communicating with one person. At a time you're communicating with so many people around you, right? And for every pair of people that you communicate, you need a key. So let's say if you're a group of n people, and let's say as a person you're trying to communicate with n minus 1 people, right? So you alone you need like n minus 1 different keys, right? So like let's say there is one person and they're trying to communicate to so many people and they all need their own pair of keys, right? So let me say it's k1, k2, k3, k4. So it's a whole lot of key management that is required, right? And that requires a lot of memory. Also another thing is the security of keys. Whom do you rely upon for distribution of these keys if you want to save some space, right? So another way to like to mitigate this problem can be you can assign like a one person or like a one authority to sort of distribute these keys, right? But then again, like controlling so many keys can be quite a challenge, right? Within people, it's like transmitting message itself, right? So to solve a problem, like you're it sounds to me like you're creating a similar problem of same stature, right? Like now previously we were managing messages, now we have to manage keys. So this can be good enough in a small setting, but like for example something like over internet where at a time so many people are communicating with each other, like symmetric key cryptography can be quite challenging, even thinking from computing power or memory power. So an alternative to this, which is quite widely used actually, is so an alternative is rather to use what is called public key cryptography.
There was a question in the chat.
Sure.
In place of using a randomly generated key for data encryption, I'm wondering if ECC may be applied. Is there a benefit to doing that as opposed to the traditional method of combining symmetric and asymmetric encryption like PGP does?
So elliptic key cryptography is an example of public key cryptography. Okay, and the advantage of using like an example of using ECC is that it offers security with lower computing power and also battery like lower battery resource usage. So even in some of like as far as I have read, I think like including Bitcoin and even Ethereum, some of these things really use elliptic cryptography these days. But yeah, I think the question mentioned about combining these two things, and you're right. Like most of the protocols also use some sort of hybrid thing. So they use asymmetric and symmetric cryptography in combination. But ECC, I think, completely falls in the category of public key cryptography. And the reason it's more, yeah, as I said, it offers quite like good security, like I would say equivalent security with some of the protocols mentioned with lower memory, lower computing power, and lower battery usage. So it's quite efficient in that sense. Did I answer the question?
Yeah, Abdullah says thank you.
Okay, awesome. Yeah, so we will see some so in this course we will see, like, it, for example, today I'll just discuss some examples of public key cryptography, and I'll briefly discuss ECC, and obviously we'll see this in much more detail in coming lectures. So yeah, so alternative to use, like, to resolve this key management issue is to go for public key cryptography or asymmetric cryptography. So it was introduced in 1975 by Diffie-Hellman and Merkle to address the shortcomings of symmetric key thing. So let's see an example. Okay, this is let's directly start with seeing some examples. So first is, it's RSA protocol, or yeah, let me say RSA protocol. So it's actually named after the people who invented it. So Rivest, Shamir, and Edelman. And it was proposed in, I think it was proposed roughly around 1970s. And I'm speaking this from memory, but I think this was proposed in 1977. Uh, just check this. This might be wrong, but please check this. But yeah, this is me speaking from memory. Anyway, so this was proposed way back in 1977, and this is quite widely used. So what's the idea? The idea is that, again, just to go back to our schematic. So again, there are two people, A and B. They're trying to communicate message, and again, the idea is A will encode it and B will decode it. But now, instead of having a single key, there is something called a public key, which is known to everyone, not just A and B. This public key is really public. Like, this is also known to our eavesdropper, right, who is trying to read the message. But now A and B have their own private keys. So let's say private key is DA and B has its own private key, say DB. And this information, as the name suggests, so DA is not known to B and vice versa. DB is not known to A, let alone anything else, right? And most of these things, most of these crypto systems, they rely on one fact, that the underlying, so the idea is that underlying mathematical problem is hard to solve. And now, when I say hard to solve, not just theoretically, but doing that in real time, right? That is hard to do. So these things rely on that, right? So for example, let's say RSA. How does it work? So let's say we have a let's say we have some sort of a bit length or a security parameter length, right? Let me call that uh, L. So let's say L is our security parameter. Or some textbooks also use the word bit length for it, or however we want to call it, right? And the idea is, like, with this, I want to generate a public key. Let's say, let me call this PK, and a private key. Let's say DA, or DB, whatever, right? So what's the idea? The idea is that I randomly select two prime numbers P and Q, okay? And these two have the same bit length or same security parameter, right? And their bit length is L over 2. After I randomly select these two primes, what I do is I compute their product. And let's give it a name. Let's call this N, okay? And I also compute P minus 1, Q minus 1. And this number, P minus 1, Q minus 1, it seems quite random when we see it first. Like, but there is a reason why we choose this product, P minus 1, Q minus 1, right? It has got to do, so this has a name. This phi is what we call Euler's phi function or Euler's tangent function. And we'll discuss this function in coming lectures where I will be discussing group theory and finite fields in detail. But the idea is, what does Euler's tangent function do? And this is some sort of an aside, just to give an explanation of where these things come from. So what does Euler's tangent function do? Phi, it takes an integer and it again produces an integer, rather a natural number. Also n is a natural number. What does it do? So phi n is basically is the number of integers between 1 and n which are co-prime to n. Okay. So just to, by co-prime, I mean that they do not share any prime factors, right? Or when you're trying to take the GCD, it will be 1. So just to give an example, let's say I have 3. Let's say my n is 3. So what is phi of 3? Okay, so I look for all the numbers between 1 and n. So 1, 2, and 3, which are co-prime to 3. Okay, so which of these things qualify? Well, obviously 1 is co-prime to 3 because 1 and 3 do not share any other common factors except 1. 2 and 3 do not share any common factors. And 3 doesn't qualify, right? Because 3 obviously shares prime factors with 3. So phi of 3 is just 2. Okay. Let's take another example. Let's take n equal to 6. And now what I'm doing is I'm looking for all the numbers between 1 and 6, which are co-prime to 6. So which of these things qualify? Let's see. Again, 1 always does. 2 doesn't qualify because 2 and 6 do have a prime factor. It's 2, right? 2 divides 6. Again, 3 doesn't qualify because 3 and 6 have a common factor. 4 also doesn't qualify because 2 is a common factor between 4 and 6. 5 does, right? So phi of 6 is also 2. Okay. So what I had before was a product of 2 primes, right? So if I give you product of 2 primes, what its tangent function is given by this formula, P minus 1 times Q minus 1. This is not like, this is not immediately obvious from the examples that we saw. We just saw 2 examples. Why this holds and everything will follow once we see basics of group theory, right? And we'll discuss this in next lecture, but I just wanted to explain where this number comes from, right? So this number that we have here, phi, which is P minus 1 times Q minus 1, this is not a randomly chosen thing. It comes from Euler's tangent function, and it's the number of integers between 1 and n which are co-prime. And the reason why this is so important, it will become clear, okay? So let's trace back. So what we had was, we started with our security parameter, and we want to generate a public key and a private key. So we randomly select 2 primes, P and Q. We compute their product and this torsion function. And now our output, sorry. And then after we do this, we select an arbitrary number. So select an arbitrary number. Say it is E, which is between 1 and n. Mm, I think I want this to be between 1 and phi actually. Yeah, not n, sorry, 1 and e. Such that, so GCD of E and phi should be 1. Okay, E should be coprime. And now, after I select E, I compute another number called D such that when I multiply D with E and I take its remainder, it should be 1 when divided with phi. Okay. So this equation that I've written right here, for people who are not familiar with this, I'll just explain this. So what this means is D times E is obviously a number, right? It's a natural number. And when I say DE is congruent to 1 mod phi, these three lines right here, they are read as congruent to. So when I say DE is congruent to 1 modulo phi, what I mean is when I take DE and I divide it with phi, the remainder I get should be 1. Okay. For example, again, this is just an aside, just to illustrate this notation. For example, 7 is congruent to 1 mod 3. Because when I divide 7 with 3, I get 2 as a quotient and 1 as a remainder. Okay. So what you see on the right hand side is really the remainder. And what you see inside modulo is the number that you're dividing it by, your divisor. Okay. Just to give another example, 5 is 2 modulo 3. Because when you divide 5 with 3, you get 2 as a remainder. Okay. So after doing all this, what are my public keys? So my output is, so my public key was that number n, right? Which so first I selected 2 primes. So let me just recall what was n. So I selected 2 primes at random PQ. I computed its product. So I put that. That's my public key. Along with that, I also declare my E. Okay. I'm happy to declare this E. Now, what I keep private is this D. Okay. Now, the idea being here that even though somebody has information about N and E, it's not easy to derive D from it, right? And why is that? Because, okay, even if I tell you N, it's really hard to find P and Q such that N is P times Q, right? So this is hard. And this relies on difficulty of something called integer factorization. So this relies on difficulty of integer factorization. And when I say difficulty, again, like mathematically speaking, theoretically, obviously, like we know that every integer can be factorized, right? Like if I give you, and obviously the like there are, you can find P and Q such that, and if it is a product of 2 primes. But hardness in the real world, it means obviously it's computationally hard to do it. It's not easy to do it in, let's say, polynomial time. And like this uses, obviously in practice how we do this is we do this with very large primes. Otherwise with small primes it's not very difficult. Like once you factorize it, P and Q, then finding this private key is not very difficult. Once you have this information of P and Q, you can compute your phi, which was product of P minus 1 and Q minus 1, right? And once you compute phi, you already know E. All you have to do is find this D such that D. So doing like the hardness really is finding P and Q. Once you do that, if somebody is able to do that, then finding this private key from public key is not very hard. So this algorithm, it really relies on difficulty of integer factorization. And if in practice, if we take these primes to be really, really large, then it's quite a challenging thing to do. So this is my information, okay? Public key and private key. Now, how does encryption work? What does it do? So let's see. So how does encryption work? So I take my message. So start with message. Let's say M, which can be, as I said, it in practice it can be a photo, it can be a video, it can be a text, but let's assume that we have converted this into a number somehow. Okay. And I interpret this as a number between 0 and n-1, let's say. Or just to not to use too many notations, let's say this is between n-1 and 0. Think of this as a number. Okay. So I already know. This n is, again, this is coming from the public key. So I already know my public key, which was this n and this e, right? So what I do is I create this ciphertext. So what is ciphertext? So I take this message M and I raise it to the power of E. Again, recall that all of these are natural numbers. So I just multiply M with itself E number of times. And I compute it modulo N. By that I mean I just compute its remainder. And this is my ciphertext. Okay. And I return this. And how does decryption work? So decryption. So I started with my M and I have transmitted this ciphertext to B, right? And what will B do? What will B do is, now what is, so B requires this private key, let's say D. So let me give this ciphertext a name. Let me call this C. So what B has to do is just, so all B has to do is to raise this C to the power of D modulo N. So what is this? So what was C? So our C was this M to the power of E modulo N. So this is rather M times E to the power D modulo N. Okay. But how were E and D chosen? The E and D were basically chosen keeping this property in mind, that when you divide it with phi, you get back 1. Okay. And this will also tell you that when you raise it to the power E times D, you automatically recover M modulo N. Okay. Like from here to here, this step, this uses group theory. Or rather, this uses group structure information. Okay. What group it is, what property are we using? Again, I'll illustrate this in because yeah, this is supposed to be an introductory lecture. We'll see this in coming lectures. I mean, this is one of my prime examples of groups, right? The things that we see. So what is the group? So speaking group, it's nothing, but it's like a set of numbers with a certain operation on them, right? So it can be symmetry, it can be multiplication, it can be addition, right? So this, so what group it is, what set it is, what operation, why does this follow? It will again follow once you see basics of group theory. But this is, yeah. So all B has to do is basically use the private key that they have and raise the ciphertext to D, and they recover their message. Okay. And again, this can be made more secure. You can add, as I described, you can add security tags to it. You can add your own signatures to it, and we can also verify that the message that they received was indeed sent from A and not from some imposter or something like that. Okay. So this is one example of public key cryptography. There are several others. There there is something called a discrete logarithm problem, and the underlying, yeah, as I said, the trust factor in these system is really that the underlying maths is quite hard to solve computationally. And yeah, this is very important, otherwise any, like, it would be easy to break, and then there is no security in these things. So it's, the other protocols are also discrete logarithm systems. If we have time in the end, I'll also discuss this, but let me discuss elliptic curve briefly. Elliptic curve cryptography here, how does it work, and just a basic idea. ECC. So before elliptic curve cryptography, let's discuss a bit about elliptic curves. What are these things? And so elliptic curve, it's as the name suggests, it's a curve, right? It's a curve at the end of the day. And every curve, like, you can think of parabola as a curve, even a straight line is a curve. It's always given by an equation, right? There are variables involved in it. You have your y's and your x's. So what is the equation for elliptic curve? The equation for elliptic curve looks something like this. So this is an example. This is an example. So we always have y square on left hand side. And on right hand side, we have a degree 3 polynomial in x. For example, let's say x cubed plus 1. But not any polynomial. Okay. What I require is that when I take this polynomial and I find all its roots, they should be distinct. I don't want repeated roots. Okay. Like, if somebody says y square equal to x minus 1 cubed, that is not an elliptic curve. This is an equation, all right. Like, this is some curve, but this is not an elliptic curve. Because x minus 1 cubed has repeated roots, right? X equal to 1 occurs 3 times. So this is not an example. This is not an elliptic curve. So for elliptic curve, the equation should look something like this. I should have y square equal to a cubic, and roots of that cubic, they really should be distinct. For example, x cubed plus 1, what are its roots? You take cube roots of minus 1, right? And they are all distinct. Okay. So uh, in general, elliptic curves equation, they look like y square equal to x cube plus ax plus b, where, yeah, having this, like, roots all distinct can be also summarized by this. So if you take the number 4a cube plus 27b square, it should not be equal to 0. This is the thing. Okay. Now, what we will be focusing in this course is elliptic curves. So we will focus on elliptic curves over finite fields. Again, what are finite fields even before elliptic curves? We'll discuss. This is planned for next couple of lectures. We'll see what are elliptic curves. What do we mean? So when I say elliptic curves over finite fields, what do I mean? So this is an equation, right? And I'm looking at solutions over these finite fields. And I'll just give an example in few minutes just to illustrate what I'm saying. So we'll focus on elliptic curves or finite fields in this course. So let's take an example of what I mean by this, right? So example. So let's take this equation, for example, and this is from textbook. This is straight from textbook. So you can actually go back and verify this or read this again. So let's take y square equal to x cube plus 2x plus 4. And I'm thinking this over a finite field f7, let's say. What is this f7? Well, this is a finite field that has only 7 members. That has 7 members. And what do these members look like? Well, it's something that you already saw before. The elements look like 0, 1, 2, 3, 4, 5, 6. So there are 7 members. And obviously, there is a way to add and multiply them and also subtract and divide. So what I do is, so how do I add and subtract them? Let's take, let's say, for example, 1 and 6. So I add them as if I'm adding natural numbers. Okay, so 1 plus 6, that gives me 7. But I don't see any 7 here. So what do? I read 7 mod 7. That is, I take the remainder when I divide by 7. So what is this? This is 0. So 1 plus 6 is actually equal to 0. Okay. And same goes for multiplication. So when I multiply 1 and 6, I just take its remainder modulo 7. So 1 times 6 is just 6. So this is how I add and multiply. Okay. So y square equal to, and this, to verify this is an elliptic curve, you can compute this number 4a cube plus 27b square. And this will turn out to be non-zero. So this is indeed an elliptic curve, right? So over f7, what are the points of this curve? Well, the points, there is always a point over infinity. Again, what does this is like, again, some mathematical concept, but we don't have to worry about this at this moment. We can explain this later. But when when x is 0, for example, when x is 0, y square has to be 4. So what are the two possibilities? Well, y can be 2 or minus 2. But what is minus 2 in this universe? Well, minus 2 is just 5, right? So when x is 0, your y can be 2 or your y can be 5. So this already gives you 2 points on this curve, right? Similarly, when x is 1, we can have 0. When x is 2, you will get 3 and 4 and so on. Similarly, we can compute all the other points, right? And obviously, there has to be finitely many points because there are finitely many possibilities for x and y. We will just plug in each value for x and see if there are any possible values for y or not. So this is what I mean when I say that we will consider elliptic curves over finite fields. Like we have a finite set of elements and we'll be looking at points over those. Now, what is also nice about elliptic curves that is quite fascinating, it doesn't happen in general, is that one can add, there is a natural way to add 2 points on elliptic curves. I mean, this doesn't make, hello? Yeah.
Yeah, I'm sorry to interrupt. There was a couple of questions in the chat.
Sure, yeah.
Abdullah was asking, when two people wish to share a private key using ECDH, they first choose a point G on the elliptic curve. Next, they multiply G by the random integers A and B respectively that each of them choose. Following the multiplication, they each share AG and BG with one another. Next, they multiply once more using their keys, ABG and BAG, respectively, and produce a shared key. But how can someone use this method if he wishes to use ECDH to share a shared key and interact with more than two people. Because while establishing the key, each participant may select a different integer.
Hmm. So, okay, just so that I get it. So there is one public key, right? And then the private keys are what like individuals have. So I think that what the question mentioned was some sort of hybrid between symmetric and asymmetric. Is that correct?
I think the question was about more than two people exchanging messages.
Yeah, so even in that setting, I mean, you will have a sort of a public key, right? And then the however number of people are involved, they will own have their own private key. So they can, depending on what cipher text they can use their own private keys to decrypt that, right? And further encrypt that to send to another person. Does that make sense?
Yeah, I mean, the way I see it, as of now, we can think of the elliptic curve method as another black box, similar to the integer factorization that you described.
Right, right. Well, I mean, I was just going to describe it. So
Yeah.
it's, yeah.
And the other question, a couple of questions more directly, what is the purpose of the inequality expression in your slide for ECC?
So inequality in ECC, I think I used inequality somewhere here. Is that correct? Yeah. I think this was probably, yeah. So the purpose is basically like, let's say you have a text message or something. You have converted this into a natural number. This inequality means that we are reading it modulo n. Okay. So we already have, so this, and this n comes from public key, right? So we are reading this modulo n. What are modulo n? These are basically remainders that one see when you divide by n. And what are the remainders one can see when one divides by any number? Like, for example, what are the remainders you see when you divide by 3? Well, you can see 0, 1, and 2, right? And then it cycles like that. So when one is dividing by n, all the remainders that you can see lie between 0 and n minus 1, right? So that's the significance. Because we are reading things modulo n, that's why we yeah, we restrict it to this. So even though your message, the original message, it can be quite long, let's say, and when you have converted this into some sort of a number, it can be larger than n, technically, right? But what I'll do is I'll read my message modulo n and work from there, right? So everything is like reading this modulo n.
Thank you.
Yeah.
The last question was one which actually I had myself,
Yeah.
which was, why was infinity added to the set? Although
Right.
it works with the equation, weren't we confined to use the finite field F7?
Right. So the idea of infinity is like we see y and x here, right? But there is also a missing variable here, and that variable is z. So why z comes from where this thing, it's so like, so this hidden variable is actually y square z equal to x cube plus 2x z square plus 4z cube. What I wrote was what we get when z is equal to 1. So when z is equal to 1, you will see y square equal to x cube plus 2x plus 4. But what happens when z is 0? So if we plug in z equal to 0, you will get x is also equal to 0. And then y can be really anything, right? So this infinity is nothing but this point 0 comma, let's say y comma 0, where y can be anything. Okay. So what we see in terms of x and y is really what is called the affine part of the equation. To see the complete picture, we have to look at this projective part of the picture. And this extra point is what we get when this hidden variable is 0. Okay. So we'll discuss this in
Okay, thank you. Yeah.
yeah. So let me just call this projective, and this is what is called the affine part of the equation. All right. Right. So just to continue, what is nice about elliptic curves is you can actually add 2 points on it, which, like, if you just stop and think about it, it's quite marvelous. Because if I give you a random parabola and I give you 2 points on it, and I ask you, like, for example, let's say, like, we have a parabola. If you take 2 points on it and I tell you add it and give me a third point, it doesn't make sense. It doesn't make sense to add points on the curve. But somehow, for elliptic curves, geometrically, they have a very nice interpretation of adding 2 points, right? So what yeah, I'm running short on time actually, but let me just explain this briefly. So let's say I take an elliptic curve. uh, let's say it looks something like this. So what does it mean to add 2 points on it? Let's say my 2 points are here and here. So what I do is I take the line joining them, okay? And then I try to extend this line till it intersects a third point. Let's say, let's give these things a name. Let's say P and Q are the original points that I was trying to add. So I take the line joining them and I keep extending that line till it intersects my curve in third point. And that point is guaranteed to happen, right? Because that again follows, because we have a degree 3 equation. So let's say this blue point is R. No, this blue point is, let's say, R. Now what I do is, third step is I take the reflection of this point across my x-axis, okay? And whatever this point is, this is my P plus Q, okay? So this is this is a visual representation of adding 2 points, visually. Now, a natural question is, like, if I give you coordinates for P and Q, can you give me coordinates for P plus Q? Yes, we can. There is a formula for addition. There is a very nice formula for addition, but it's quite complicated to write it down. And I won't try to write it down now because frankly, these are just long equations, and it's more interesting to see these things visually. But we will work with equations also at some point. But yeah, the overall point was that there is a very natural way to add 2 points on elliptic curves. So how do we use these things to generate elliptic curve key? Let's say, so let's say we have an elliptic curve over a finite field. Let's say FP, okay? And suppose I have a point, P is a point on E. And when I say a point, think of, like, we already have an example, right? So think really of a coordinate like x comma y. So P is a point on an elliptic curve. And say that when you add P to itself n number of times, we get back what we call 0, or really the identity. Now this thing again is slightly technical. It comes from group theory. But, like, to give an example of an addition, like, let's go back to our finite, not addition, like, for example, this, let's go back to F7. Like, if I take 2, right, and I add it, like, let's say, what is 2 plus 2? 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8. 8 plus 2 is 10, 10 plus 2 is 12, 12 plus 2 is 14. So I get back 0, right? So when I add 2 7 number of times to itself, I'll get back 0, right? So that's, and 0 is the identity. So that's what I mean. When I add the point to itself n number of times, I get back the identity, and n is the number. And no smaller number than n would work, right? For example, for 2, no smaller number than 7 will actually work. So this is what I mean. So I take all the points. So I take P, take 2P, 3P, all the way up to n minus 1 times P. And also, this infinity is always there. Let's denote this by, and this is these angular brackets, they basically mean group generated by P. Right. So these things, so all these things, right? These, so this prime P, so this small prime P, this elliptic curve, this point and its order are what you can say it's, let's give this a name. Let's um, like how we had security parameters, let's just call them parameters, right? These things are what we will use to generate. So the idea is to, so we want to generate public key and a private key. So within these parameters, how do we generate public key? So first of all, we select number. Let's give this a name. Let's say D, which is between 1 and n minus 1. All right. And then I compute this point, which is also on my elliptic curve, D times P, which is basically I just add P to itself D number of times. Okay. And this Q is my public key. And this D is really my private key. Now, the idea being that if somebody, even if somebody has information about Q and P, it's not easy to recover D. If I just give you 2 points on elliptic curves and I tell you, if I give you Q and P, right? And I tell you, tell me how many times you have to add P to get back to Q, that information is not very easy to recover. So again, the mathematical hardness is that recovering D from Q and P is hard. This is the mathematical hardness that we rely upon. So these are our keys, and how does encryption work? So again, so encryption. So again, I have my security parameters. Let's say that prime, elliptic curve, my point, its order. I know my public key and I know my message M. Okay. So I want to produce a ciphered text, right? So first of all, I represent, so the first task is to represent M as a point in, or rather think of M as a point on my elliptic curve, which now I'm thinking over finite field. Second step is to select a number k between n minus 1 and 1. And again, think of these things modulo n. Third step is compute. So add p to itself k number of times. Once we do that, also compute. Oh, let me write this clearly. So compute my message plus k times this q. Q is now my public key. and I return this k times p and m plus k times q as my ciphertext. So basically, from this p and q, the choice here is this k, right? And I'm returning this using the technique of adding points on elliptic curves, which we'll see, like what are the equations, how do we do that, and everything. And how do I decrypt it? Because I should, like, no algorithm is complete without decryption. I should also know how to recover my message. So decryption, so what I do is I compute C2. By C2, I just compute m plus k times q minus d times k times p. I know my d, right? D is my private key. So I already know that. Uh, and what was q? If you just go back, q is just d times p, right? So this is just m plus k times q minus k times q. So I just get back m, right? So I have recovered my message. So,
There was a question from Cheng.
yes.
Any reason why M plus RQ instead of other operations?
By other operations, do you mean like multiplying 2 points on elliptic curves? I don't know how to do that. The reason we are adding is because we know how to add points in elliptic curves. Geometrically, there is a way to do that. Addition, subtraction, I mean, they go hand in hand, so to say. Multiplication, I don't know how to multiply 2 points on elliptic curves. I don't know what it means, and so does division. Okay, so the reason, yeah, again, these things are basically all these things, M, Q, P, these are points on elliptic curves. And since I know how to add points on elliptic curves, like we have a mathematical theory for that, that's why I'm using these things. Other operations like multiplication, I mean, I don't know how to multiply 2 points on elliptic curves. So, yeah.
Thank you. So that's really this nice property that the elliptic curve has.
Right, because elliptic curves, yeah, this is indeed something very special about elliptic curves. Like we know how to add points on this. Like geometrically, this is just a geometrical representation or visual representation that I gave. So if you take 2 points on elliptic curves, you just take a line joining them and try to extend it till you find a third point where that line intersects, right? And take the reflection of that point. So the reflected point is my addition, or what I call p plus q. And that, since we know how to add, we can use them now to generate our keys and my ciphertext and so on and so forth. Yeah. So that's why addition, because we know how to add points on ellipticals. I don't know how to multiply. Maybe there is a way to multiply, but I don't know. Yeah. Like when I say I don't know, I mean like I don't think that there is mathematically we know how to multiply 2 points. Right. So yeah, using these keys, this is how we encrypt and decrypt. We have recovered them, and yeah, just sort of a basic of how elliptical cryptography works. So yeah, this is mostly what I wanted to say today. In the next lecture and coming at least 2 to 3 lectures, what we'll see is we'll discuss more of group theory, finite fields, and yeah, then we'll move to elliptic curves. We'll see more about them, and what we discussed in a nutshell here about affine and projective part, we'll see in more detail, like what is this projective part, where does this infinity come from, and so on and so forth. Okay, so let's end for today here.
There was one last, a noob question. Why is RP needed?
Why is a point needed?
Why is R times P needed? It was the question.
R times P. And like, are we talking about this notation here?
I guess the question is, yeah, I'm not clear what R and P are in this question.
I mean, if we are talking about this notation right here, it's I can write it again. It's not RP. It's so it's F. F stands for finite field, and I just use a double line just to capitalize it, and then F sub P. This denotes finite field that consists of P elements. Like I gave an example of F sub 7, right? That has 7 elements. So 0, 1, 2, 3, 4, 5, 6. Like for FP, we similarly have P elements. 0, 1, 2, 3, all the way up to P minus 1. I
The,
hope the question was about this. I'm not sure if the question was about
the question is clarified. RP is on the second to last slide,
second to last slide.
towards the bottom.
KP. KP. It's K. Oh, it's small k.
Okay, so yeah, so it's a misunderstanding.
Yeah, k times p. So we have selected a number and we have added this number to itself. Why is it needed? Okay, let's just forget. So forget. Let's just say p maybe. So p plus q, and then I mean the idea is yeah. Let's say even if we remove this k as a parameter, right? So what we will have, you will have p, right? And then we will compute this m plus q, and then you will simply return p times m plus q, right? And then you can always use your private key to get rid of it. So what k does is, like, theoretically this algorithm would work without introducing this k, right? But this k adds a layer of security, if I can say that, right? Because p is already your public, it's already in your public domain, right? So like transmitting everything directly in terms of just p would be like, everything is still in terms of p, but I think in my understanding what this k is doing is it's adding an extra layer of security or an extra layer of unknown information that just makes your algorithm more secure. Otherwise, theoretically, you're right. Everything would work perfectly even without k, or you can just like take k to be 1, for instance. Yeah, things would work, but I think this k adds an extra layer of security, which is important. So
Thank you.
yep. Okay, yeah, I mean, yeah, as I said, like, I think let's stop for today, and then we'll continue with group theory on next lecture.
Right. Thank you for the bird's eye view of what's to come.
Yeah.
All right. As you can see, I'm still in the lobby.
Oh, hi.
Hi. So well done. I'll stop recording. So if any of you want to carry on, your discussion and these things, that's all right. But well done, for the first session, and I look forward to seeing everybody back again. So yeah, well done. I'll stop recording, and then later I'll put the recording will be available on YouTube for everyone else to rewatch, and I will send you a follow-up email.